Hello and welcome to the 50th lecture in this series. Towards the end of the last class, I was discussing an example involving seeing how pullbacks look like when we take pullbacks of certain very specific symmetric and alternating tensors. So we did the case of the inner product, and then now we are looking at the determinant. So here the claim was that when I take the determinant, the tensor given by the determinant, then the pullback under a linear transformation, you will get back the same form or tensor, except that it will be multiplied by this constant det t. And I was in the process of proving this. So let me resume with that. So I claim that this equation that I wanted to check, this one, instead of working with all vectors in Rn, it's enough to assume that V1 is E1, Vn is En, etc. A1j, Ej. Right. So without loss of generality, we can assume that these are this, because in general we have this, any Vi can be expanded like this. Now note that T star alpha acting on V1 Vn actually, let me write it like this. So here's a separate statement that I want to make here, which is that note that if T is from V to W and alpha is a alternating K tensor on W, then T star alpha, the pullback, is an alternating K tensor on V. This is again something which is immediate from the definitions, so I won't prove this, it's quite straightforward. Similarly, if alpha is an symmetric K tensor, which I denoted by SKW, then T star alpha is an SKV. So in short, the property of alternating or being symmetric is preserved under taking pullbacks. Now keeping that in mind, this T star alpha, what I have here, this is alternating, and the right hand side is just alpha multiplied by a constant. So this is certainly alternating by assumption. No, not by assumption, because alpha is the determinant. So both sides are alternating tensors, and we have to check that they are equal. So it's enough. So in that case, so it's immaterial actually whether that I'm dealing with T star alpha, determinant, and so on. I might have as well, let's call it eta, and let's call this whole thing as lambda. The specific nature of these tensors is not that important. I just have two alternating K tensors and I want to check that they are equal. So what I do is, if I take either eta or lambda and act it on V1 up to Vk, then I'll have this, then I'll plug in this expansions in terms of the basis vector, standard basis, Akj, Ej. Now I use the, well, at this point the notation becomes a bit messy because I can't use the same j for all of these sums. So let me call the first one as j1. So j1 itself runs from 1 to n, and here I would have to call it jk equals 1 to n as well. So here I would have to say jk. And here I would have to put k as well. And with the point is that after that's not the main thing. The main thing is that using multilinearity, I'll get a sum over j1 all the way up to jk. I club all these coefficients together, product of this akj, then eta of ej1 ejk. By the way, here I am working with k, even though ultimately I am going to take k equals n. That's going to matter. So now this is what I have, and then in this expansion, in this sum, this ji's, the indices ji's can very well equal one another. But notice that because of this assumption that if eta is alternating, the moment if one ji equal ji1 equal to ji2, then this will be 0. So the only way this the terms in the sum will survive, or if all the j1, j2 all the way up to jk, they are all distinct. That is in general. If k equals n, then what happens is that the same remarks apply. So the only way this will survive is if all these indices ji are distinct. So in other words, the only surviving terms in the sum are of the form, when I say surviving, I mean non-zero, are of the form eta ej1 ejk, where ja is not equal to jb if a not equal to b. And in other words, this would be i.e. j1 ejk. Oops, not e is immaterial, it's just the indices which matter. So j1 jk is a permutation of 1. Now I can drop, so I should no longer keep k. So j1 jn. So here 1 up to n. So this index set is just a permutation of this 1 to n, because they are all distinct and there are exactly n of these, and each one is lies between 1 and n. So therefore it's a permutation of the set. So in other words, so this is, but then if this is a permutation, and since we have assumed that eta is alternating permutation, let's call the permutation sigma. So when I say this is a permutation sigma of this, what I mean is j1 equals sigma 1, jn equals sigma n. eta is alternating, we have seen that, then this thing here, ej1 ejn will be just -1 to the power sine of this permutation times eta acting on E1 up to En. So in short, what we are saying is that this, we started with eta V1 up to Vk. Then we use multilinearity to break it down to an expression of this type to get a sum here. And then we looked at each term in the sum. The coefficients a1, aj are not, they're fixed by the vectors, but what is of interest is these terms here, eta, ej1, etc. And what we have seen is that each of these terms is essentially -1 to the sine sigma eta E1 En. So in other words, therefore the conclusion is that, therefore if we have if eta and lambda are two n forms on Rn, actually Rn is not that important, but since I'm working with, in this example we are working with Rn. So if eta and lambda are both in alternating n tensors on Rn, and eta of E1 up to En equal to lambda E1 up to En, then eta V1 Vn equal to lambda V1 Vn for all V1 up to Vn and R. So which is what we wanted to claim, that if they agree on this basis vectors, then they agree for all vectors. And this eta and lambda are what, T star alpha is eta, the right hand side is lambda. So that's reduced it to this case of looking at a basis vector, but so let's see what happens for a basis vector now. So I want to look at T star alpha, alpha is the determinant on acting on E1 up to En. This is alpha acting on TE1, TEN, which is just determinant of, because well, before that I should write it like this, perhaps determinant of TE1 square brackets TEN. This is just determinant of T. After all, TE1 will give me the first column of the matrix of T, etc. So I get determinant of T, and which is and the right hand side was determinant of T multiplied by alpha acting on E1 En. This is determinant of T times determinant of E1 En. This is just the identity matrix. So this is also determinant T. So both sides are equal to determinant T, and one is done. So in short, so this, whatever the calculations we did in this are very useful for later on, and I'll have occasion to refer back to this example subsequently. So now I want to describe an important, so we will focus only on alternating forms. We'll in this course, symmetric form tensors will not play any subsequent role. So, however, these alternating tensors are very important, mainly because of the connection with determinant. Now, what I want to do first is, I want to describe a way of getting, it's sometimes called anti-symmetrization. Anti-symmetrization. So, I want to start with any multilinear K tensor or form, and then out of that I want to get an alternating one. This let's call this map alt. So let's see how one would go about this. For instance, let's say, right, so example, suppose I start with, let's say alpha is a multilinear, it's a bilinear form, in other words multilinear 2 form, and I want to get an alternating 2 form out of this. So what I can do is, let's define alpha tilde of VW to be, let alpha tilde of VW to be alpha of VW minus alpha of WV for all VW and V. Now, if I do this, it's clear that this alpha tilde will still be a multilinear form, and the important new thing is that alpha tilde will be alternating. Alpha tilde of VW equal to negative of alpha tilde of WV from the way it's defined. And it's not the case that we'll always get something interesting out of this. You can start with some alpha and end up getting 0, the trivial alternating form 0. In fact, that you can say when exactly that happens, if the alpha that you started with, for example, was symmetric, then note that if alpha is symmetric, for example, if you started with the inner product, if you start with a inner product, there is no the inner product. So if alpha is symmetric, then alpha tilde is the 0 form. And moreover, alpha is symmetric, this happens, and if alpha that you started with is already alternating, then, well, so you would alpha of VW, alpha tilde of VW would be equal to, so this, the second term here would be the same as the first term, but get a minus sign. There's already a minus sign, so it becomes plus. So I'll end up getting 2 times alpha VW. Alpha tilde is 2 alpha. So that's why it's nicer to put, I should put a half here. If I put a half, if I defined alpha tilde as half, if I put a half like this, then I'll end up getting alpha tilde equal to alpha if alpha is alternating. So this serves the purpose, Namely, we start, at least for two forms, it's quite easy. So I just do this and I get what I want. So ideally, I would like to get, I would like to have a map from start with any multilinear K form and end up with an alternating K form. And this should have the property that if whatever I start with is already alternating, then it should not change like this, except for this constant of 2. And there is a way of going about it that is called antisymmetrization. So for any K, so for 2 we have already seen what it is. For any K, so we can define this map alt alpha is 1 over K factorial summation sigma in Sk. So I have to, the way it's defined, you define it by its action values, just like we did it for K equals 2. So I want to see alt alpha acting on V1 up to Vk, and this I define to be 1 over K factorial alpha minus 1 to the power sine of sigma, and then I put a then I see what alpha of V sigma 1 is, V sigma K is. So this should remind us of something that basically it should remind us of the definition of the determinant. The determinant is also exactly defined in like this, determinant of an n cross n matrix. Here the difference is that this K need not equal to the dimension of the vector space. Even if K is less than that, we can define it like this. We'll see what happens. We'll see that if K is bigger than n, then the right hand side is automatically 0. And so the only interesting ones are when K is less than or equal to n. Right. So this is the definition. And note that if K equals 2, we recover alt alpha, which I called alpha tilde, except for the factor of this K factorial 1 over 2 and then, so essentially there will be two S2. So I'll be essentially looking at permutations. S2 is permutations on two letters, which is it consists of just two elements. One is identity, the other one is the transposition, which interchanges 1 and 2. So for the identity permutation, of course, I'll just get alpha of VW, and for the transposition, I'll get a minus sign, and then WV. So this is half alpha tilde. And in general, so the main properties of this are the following proposition. At least for now, let's know the goal was to actually get something which is in AKV. So that should be the basic property. So for any alpha in LKV, alt alpha belongs to AKV. And the second thing we would like is if alpha is already an alternating form, then alt alpha should be equal to alpha. We don't want a process which will change something which is already alternating. This is a natural thing to require, and it is in fact satisfied by this definition of alt alpha. So let me check the first one quickly. Right, so I would like to know that alt alpha. So I'm going to use, remember we had various equivalent characterizations of the property of being alternating. One of them was that if let start with a permutation, let sigma belong to Sk. Then we want to check if sigma times alt alpha. We want to see what this is. If this alt alpha is indeed alternating, then we should end up getting -1 to the power sine sigma times whatever we started with, which is alt alpha. So let's see if that happens. I'm going to just act it on k vectors. Now this, by definition of the sigma multiplication, is alt alpha acting on v sigma 1, v sigma k, and this, now I go to the definition of alt alpha. This is 1 over k factorial. So I've already, so let's call it sigma naught. Sigma naught. So here we have fixed a specific permutation sigma naught. In the definition of alt alpha, I need to consider all permutations. So I'll index them by sigma. And this would be, well, -1 to the power sine sigma, and then essentially alt alpha acting on v. Now here it is sigma multiplied by whatever index you have here, you just act it on sigma of sigma on that. V sigma 0 k. Now here is the main point, that for any sigma naught in Sk, if we look at these products, sigma naught, sigma naught, in other words, oops. So here I'm evaluating that on sigma naught in this and sigma naught. So here what I'm doing is evaluating this sigma naught on 1, 2, etc. Now this is anyway sigma multiplied by sigma naught is again a permutation lying in Sk. So This set will be just a permutation again, and the question is, how do we rewrite this sum that I have here, so that I can take out the, I'll get the right sign out. I need a -1 raised to sine sigma naught rather than -1 raised to sine sigma. So we'll discuss that in the next lecture. So we'll stop here for now. Thank you.